Welcome to Paving's webinars for the pavement community. My name is Andrew Braham, and today we'll be talking about evaluating the aggregate size effects on dynamic modulus using a grayscale analysis. Now, this work was primarily done by Dr. Sadie Casillas and Dr. Iram Morales-Vega, and it's based on a presentation that we did that was kind of a fun side project. And the side project was titled Evaluating Aggregate Size Effects on Dynamic Modulus Using a Gray Scale Analysis. And this was originally presented at AAPT back in 2019, and it was published in that journal as well. And if you want to learn a little more about Dr. Casillas and Dr. Morales-Vega, you can take a look at their LinkedIn profiles in the link below. Now, talking about aggregate size effects, dynamic modulus, and grayscale analysis, let's start with a broad background. Aggregate comes in various types and sizes, and you can see a nice image here of some 3/8 inch aggregate, number 4, number 8, number 16, and number 30. And as you can see, when you're going from the left to right, the aggregate sizes get smaller. And as you go down even further, you get to passing the number 200 sieve, and then it's all put together by Asphalt binder. And what you need to do is you need to take these different sizes of aggregates and also different sources of aggregates and blend them together, trying to balance both performance and cost. Now, when we think about dynamic modulus, the intent of dynamic modulus is to simulate pavement deformation due to traffic loading, and it's also an input into mechanistic empirical designs for pavement structures. The point of the test is to apply repeated loads at multiple frequencies, and you measure the recoverable strain, and this is what allows you to calculate permanent deformation. The standard configuration for the dynamic modulus test is 100 millimeter diameter samples that are 150 millimeters in height, and this is called the Uniaxial dynamic modulus, and you can see an image of a sample on the right. And this is a key test that can be performed in the Asphalt Mixture Performance Tester, or AMPT. So there's been a lot of excitement and use around dynamic modulus over the years as inputs to pavement design procedures and also being a key fixture in the AMPT. And the question that we wanted to ask in this research is, does the aggregate size within these samples impact test results? And this kind of got us around to thinking about what's called representative volume element, or RVE. And RVE can be defined as the smallest size at which specimens are statistically representative of a heterogeneous material as a whole. Now I'm going to turn to a colleague here to talk about how asphalt mixture RVE is dependent on the nominal maximum aggregate size. And this is shown very nicely here by a paper by Kim et al. In 2019, showing a test sample in the testing chamber, zooming in on that test sample and looking at the TRVE, which they called the trial representative volume element. And if you look at these 4 different grids, you can see how the aggregate is different sizes within these grids. In grid number 1, there's that single aggregate that takes up quite a bit of the grid. But if you go down to grid number 4, where you take a larger area of the sample, you can see that one aggregate no longer dominates, and it's part of a cluster of more aggregates. And you can look at this as going from 1 to 4 as increasing the size of the TRVE, or the trial representative volume element. And as you're going from 1 to 2 to 3 to 4, you are converging on the RVE, the actual representative volume element. And there's a possibility that your mixture characterization can change as you're going from 1 to 4, because maybe 1 isn't really representative of the mixture behavior because of that one single aggregate. But when you get down to 4, you have a representative specimen in order to test to get actual results. So this concept of representative volume element is quite important when we're thinking about test sample size. So we've talked about aggregate size, we've talked about dynamic modulus, we've talked a little bit about RVE, Now, how does the grayscale analysis fit into this work? Well, a grayscale analysis is where you take a picture of a sample and you measure the change of pixel intensity from 0 to 255, so over 256 levels. And 0 is completely black and 255 is completely white. And there's been some nice previous research on this, specifically around volumetrics-based global minima, or VGM, and I would encourage you to take a look at Zulu et al. In 2008, who did a lot of work to identify the boundaries between the air voids and the asphalt binder in a mixture, and to identify the boundary between the binder and the aggregate in the mixture. So hot mix asphalt is composed of asphalt binder and aggregate, as we saw previously, and there's also air voids within that structure. And so this previous research looked at, can we use a grayscale analysis to identify the boundaries when we're seeing an air void in an image, when we're seeing a asphalt binder in an image, and when we're seeing aggregate in an image. Now looking at that, what are some of the RVE baselines? Well, RVE baselines for dynamic modulus, remember the standard configuration is 100 millimeters by 150 millimeters. If you take a look at ASTM D3497, which is a dynamic modulus test that was actually withdrawn in 2009, but does have some pretty specific guidelines about dynamic modulus, the minimum diameter of a sample from ASTM D3497 is 100 millimeters. And the maximum RVE is 4-to-1 ratio for specimen diameter to nominal maximum aggregate size, which means you could put 4 nominal maximum aggregate size aggregates next to each other in a sample, and they would all be able to fit side by side within that 100 millimeters. And if you use that maximum ratio with your diameter of 100 millimeters, 25 millimeter would be your maximum nominal aggregate size for dynamic modulus. Now, if you look at a little more current standard, AASHTO T342, it explicitly states that 37.5 nominal maximum aggregate size is the maximum aggregate size that you can have in your sample. Now, I do want to make a little side note here. I've gone over dynamic modulus relatively quickly. If I can make a recommendation, if you're interested in learning more about dynamic modulus, go over on YouTube to Dynamic Modulus of Asphalt Mixtures and Binders by Dr. Eamon Kutai. And he did an excellent presentation describing the test, and this is a screenshot from that presentation. So excellent video. Getting back to representative volume element, you can see how ASTM and AASHTO both have recommended nominal maximum aggregate size for the maximum size of an aggregate in the sample. But there really is no established method to determine representative volume element in the lab. So this is an established test for dynamic modulus, but what if you're creating a new test? Is there a way to try and establish a representative volume element in the lab for any test? And that's what we really set out to do. So our research objective was to use a grayscale analysis to identify nominal maximum aggregate size and to achieve representative volume element across 3 asphalt concrete modulus lab testing geometries. So you could potentially use this procedure on new tests, but what we decided to do was use this procedure on 3 existing tests, all of which test dynamic modulus of asphalt mixtures. In order to do this, we looked at various aggregate sizes and 2 types of asphalt binders. So looking at the very low end, we had a 4.75 nominal maximum aggregate size aggregate blend, and we used both a PG 64-22 and a PG 76-22. And these are 2 asphalt binders that are typically used in Arkansas. And the 64-22 is a neat asphalt binder, and the 76-22 is a polymer modified asphalt binder. So we used 2 different asphalt binder types. We used a nominal maximum aggregate size of 4.75 millimeters, and then we also took those 2 asphalt binder types and we looked at nominal maximum aggregate sizes of 12.5 millimeters, 25 millimeters, and 37 millimeters. So we had 4 different aggregate sizes, we had 2 different types of asphalt binder, So we had a total of 8 asphalt concrete mixtures evaluated in this study. And we took these 8 asphalt concrete mixtures and we put them through 3 different lab modulus geometries. So of course we used the Uniaxial dynamic modulus or E-star geometry following AASHTO T342. This is the standard geometry. The samples are 100 millimeters by 150 millimeters, and the baseline maximum nominal aggregate size is 37.1 based on just the standard. For the indirect tensile dynamic modulus, or the IDT dynamic modulus, this follows what is now AASHTO TP131. This is a provisional standard, so if you're watching this, it may actually be AASHTO T131 now. The P may have been dropped. But these sample sizes are 38 millimeters thick by 150 millimeters in diameter. And the baseline maximum nominal aggregate size for an IDT configuration is 14.1. And then finally for the torsion bar shear modulus, or a G-star test, so the first two are E-star, the second is a shear modulus, which is G-star. We followed ASTM D7552, and these samples are much smaller. They're 6.5 millimeters by 50 millimeters, and the baseline nominal maximum aggregate size for this configuration is 2.4 millimeters. For the uniaxial test, we ran it at 5 temperatures from minus 10 degrees to 54 degrees Celsius, and we ran it at 6 frequencies from 0.1 to 25 hertz, which is following the standard. For the IDT, we ran it at the same 5 temperatures and the same 5 frequencies, so the uniaxial configuration and the IDT configuration are actually the same here. Now, the torsion bar is a little more involved. It actually has 8 testing temperatures from minus 10 to 60 degrees Celsius every 10 degrees, and the frequencies go from 0.03 all the way to 15 hertz. So these are the temperatures and frequencies used for the 3 testing geometries. Now, in order to utilize the data from the dynamic modulus, you create master curves. And the master curve generation standard followed was AASHTO R62, which is where you construct a composite curve. And this composite curve uses reference temperatures and reduced frequencies. And I do want to give a shout out to Dr. Shu Yang, who in 2017 synthesized these procedures to supplement AASHTO R62. And you can see an example of why here. So following R62 to the letter, you get your 4 shifting coefficients, alpha, beta, gamma, and delta, as shown. But you can see the isotherms. There's 5 sets of isotherms. Those are the 5 testing temperatures. And you can see those isotherms do not overlap. And this is not desired because you want to have the temperatures overlap based on the reduced frequencies. So going through multiple iterations outlined by Dr. Yang, you can see that by changing those alpha, beta, gamma values, you start actually changing the shape of the curve. And by going through the full procedure, you can get a very, very nice dynamic modulus curves where the isotherms fully overlap, and the reduced frequencies go from about 10 to the minus 6 to 10 to the positive 4th or 5th reduced frequency. And if you want to hear more about this, there's actually a Pavinar that we recorded on it, and the Pavinar is titled Correlating Field Performance to Lab Dynamic Modulus from Indirect Tension and Torsion Bar, which was released on August 2nd, 2020. And that goes into all the details about this procedure. But the point is that we're using a revised procedure in order to get those isotherms overlapped. Now here is an example of the curves for the uniaxial dynamic modulus. And what we did is we zoomed in on the bottom portion and the top portion of those reduced frequency curves. The bottom portion is where the mix is softer, so these tend to be at warmer temperatures or lower loading applications. So the left side can kind of be thought of as what happens to the mix during the higher temperatures, lower rates of loading, so potential rutting susceptibility. And then on the right side is the higher dynamic modulus values, which is at the lower test temperatures and higher frequencies, which kind of make you start thinking about what happens at the lower temperatures, so the stiffness of the mixture at those lower temperatures and higher frequencies. So for the uniaxial dynamic modulus, this is the standard testing configuration. At those higher temperatures and lower frequencies, the aggregates really dominate. And this means that the aggregate sizes, the aggregates are performing as they need to be doing. And also all polymer modified mixtures are stiffer than the neat asphalt binder mixtures. So with this standard configurations, both in regards to the nominal maximum aggregate size and the asphalt binder type, the findings really matched expectations. And this is what was expected. Now looking at the IDT dynamic modulus, it starts kind of giving some more interesting results. The stiffnesses are 50 to 70% lower than the uniaxial. So if you go back to the previous slide, you can actually see we shifted the y-axes on both the left and the right side. So the stiffnesses are quite a bit lower, and just as long as they're relatively lower, there shouldn't be a problem. There could be some sort of geometric shift factor. But the mixtures ranked in order except for the 37.5 millimeter mixture at the higher frequencies and lower temperatures. And this is kind of a warning sign, because if one of the aggregate sizes at the extreme starts falling out of line, this made us start thinking, is perhaps the 37.5 millimeter mixture too large for the IDT, because the data is no longer falling along the expectations that we expected to see. Now, going down to the smallest testing side, the torsion bar shear modulus, at the low temperatures and the higher frequencies, so on the right side of the curve, the polymer modification ranking is really not clear. And at 37.5, 25.0, and 12.5 millimeter nominal maximum aggregate sizes, the curves are actually quite similar, and the only consistent trends are seen at 4.75 millimeters. So here we can ask the question, are the 37.5, 25, and 12.5 millimeter nominal maximum aggregate size mixtures too large for the small torsion bar? So this is one way to look at the dynamic modulus data, is through these standard dynamic modulus reduced frequency curves. But we also took another way of looking at this analysis, and this is by comparing the geometries in the nominal maximum aggregate sizes. And you can see where we have the uniaxial on the x-axis and the IDT on the y-axis, and we just basically did a plot of equality. And if these two tests were showing the exact same behavior, then all of the data points would line up along that middle dotted line along the line of equality. And what we did is we took the middle dotted line, which assumed equal tests, and then we did plus or minus 1 standard deviation. And this is just to get an indication, are the two geometries starting to diverge at any points? And you can see here that the 37 millimeter nominal maximum aggregate size, which is these triangles, actually fall outside of 1 standard deviation, which means that at a 95% confidence, they are statistically different. And we can do the same thing with the torsion bar on the y-axis and the IDT on the x-axis. So the smaller test is always on the y-axis and the larger sample is always on the x-axis. And you can see here a lot of the data points start falling outside there. Almost all of the nominal maximum aggregate sizes fall outside of 1 standard deviation, which means they're statistically different. And the ones that are closest to the -1 standard deviation line there are actually the 4.75 millimeter nominal maximum aggregate size. So when we're plotting these two different sizes against each other in these plots, we feel that data within the region of 1 standard deviation, either plus or minus, could be an indication that you have an appropriate nominal maximum aggregate size for that configuration. But then when they start shifting outside of that plus or minus 1 standard deviation, maybe there should be a warning light that goes on that the geometry is not appropriate for the nominal maximum aggregate size. So all of our discussion to date with data has simply been on looking at the test data from the dynamic modulus tests. Now let's start getting into the grayscale analysis. And the point of this paper was to look at these three different geometries to see how they behave, to do this preliminary analysis, but then actually to take pictures of these samples and use a grayscale analysis as a geometric factor to define representative volume element. And what we're hoping to see is that the grayscale analysis could correlate to those dynamic modulus tests that we just talked about, the test results that we just talked about. And if this is possible, then instead of actually running a test, perhaps we could simply take a picture of a sample for a test to see if we can accept or reject a potential configuration or test size based on violating a representative volume element. And it's really nice to kind of go back. You already saw this image on the title slide, but this is the uniaxial configuration, the torsion bar configuration, and the IDT configuration to scale. And you can see how much more material is used in that uniaxial test versus especially the torsion bar test, but also the IDT test. So how did we get these images for the grayscale analysis? Well, for the uniaxial configuration, we had 5 total images. So what we did is we faced the sample toward us, we took an image, we rotated 120 degrees, we took an image, and then we rotated 120 degrees and we took a third image. So there are 3 images taken of the sides of the sample. And essentially this means that the entire sample was captured twice through these 3 images. We also took an image on the top and the bottom of the sample. So if you take a look at a dynamic modulus sample, it's cored out of a gyratory compactor sample, and then you trim it on the top and the bottom, so all the faces are actually cut exposed aggregates. So there's 5 total images, 3 along the sides and 1 at the top and 1 on the bottom. The IDT configuration is a little different because this is a slice of a superpaved gyratory core. There's actually only 2 images taken, one taken of each cut face. So the front of the IDT sample, you flip it around and then you take an image on the back of the IDT sample. And then for the torsion bar configuration, we have a 2 scale sample on the right, but we also have a more zoomed in sample on the left. And we had 6 total images, and it's kind of more similar to the uniaxial configuration. There's 4 sides of the torsion bar, so one cut face on each side, and then there's a top and a bottom that also has a cut face. So there are 6 total images for the grayscale of torsion bar. And then we are able to run a grayscale analysis. So remember, 0 is black, 255 is white, and you can see here the grayscale analysis for 4.75 for a neat binder, 12.5 polymer modified, and 37.5 also for a neat binder. These are simply shown for demonstration purposes to see what grayscale intensities dominate in these samples. And the thing that pops out most, and we'll talk about this more throughout the presentation, is on the right side there, you can see that very high value at 255 for the 37.5 millimeter nominal maximum aggregate size sample. And that's because you have these very large white aggregates. We use limestone, so we have these very large white aggregates, and that really dominate the sample faces for those larger nominal maximum aggregate sizes. Now, kind of digging deep into this graph, on the left side is the asphalt binder and the mastic type material. And on the right side, as I mentioned, is this limestone aggregate. So as we go through this presentation, we will see how we're going to use kind of these 2 regions to look at how much asphalt binder and mastic is in a mix, and then how much aggregate is in a mix, and how can we use the grayscale analysis in order to analyze that. And in order to do this, we leverage National Instrument Vision Assistant software. So taking just one of those curves and breaking down the process we went through in order to analyze the grayscale analysis, basically one of the main takeaways was called the mean value weighted average of the intensity level. So this is basically just saying what is the average grayscale intensity level based on this distribution that you see. It's kind of like a particle size distribution. And we also identified some threshold values, and we went back to Zalou et al. From 2008 and specifically looked at the aggregate to mastic, or A-M ratio. And he established the mastic threshold at 107 and the aggregate threshold at 158. So if you recall, they determined that anything below 107 could be considered air voids. Anything between 107 and 158 could be considered mastic, and anything above 158 could be considered aggregate based on a grayscale intensity level. So this is what Zalou et al. Established as the three different regions of the grayscale curve. And what we did is we actually combined the air voids and mastic, and this is what we called the A/M ratio. So when we start talking about the A/M ratio later on, this is the air voids plus the mastic, and it's everything below 158 grayscale. And then we assumed everything above 158 was simply an aggregate. And what we did is we took the average grayscale intensity curve for all the images taken per configuration, and then we combined the two binder types in order to isolate the influence of aggregate size. We assumed that the polymer versus neat asphalt binder didn't affect the grayscale analysis, so we combined the two binder types. And this is what we came up for the uniaxial grayscale analysis. So you can see on the left-hand side here, we have all 8 mixtures from the 4.75 nominal maximum aggregate size neat binder all the way down to the 37.5 polymer modified mixture. And we kept the T1 and T2 levels established by Zalou at 107 and 158. So everything to the left of that 158 we considered the mastic. Everything to the right of the 158 we considered the aggregate. And what we did is you were able to take the number of pixels under those curves for the aggregate, and we divided it by the number of pixels under the curve for the mastic, and that is the A/M ratio. So A/M is the aggregate to mastic ratio from the grayscale analysis. So that's the curve on the left. Now pivoting to the table on the right, you can see this is the data for the uniaxial configuration for the dynamic modulus. And you can see that as the nominal maximum aggregate size decreased, the mean grayscale intensity level value also decreased. It went from about 112 and 118 down to 91 to 58. The aggregate to mastic ratio also followed that same trend. And it doesn't quite decrease. There's actually a little bit more of a parabolic shape where the 25 millimeter nominal maximum aggregate size has the maximum mean value and A/M. But in general, you can tell as you go down, especially to 12.5 and 4.75, those numbers start dropping. We also include the standard deviation on there to give you an indication of the variability of the data that we're looking at. So our conclusions from this uniaxial grayscale analysis is that the gradation does have a large influence on the A/M, and the binder type has a minimal influence on the A/M. Now pivoting to the next geometry, the IDT grayscale geometry, again the same configuration here. You can see the curves on the left and then the table on the right, and you see a very similar trend where there seems to be some sort of peak value, and this is more apparent with the IDT specimen size at 25 millimeter nominal maximum aggregate size. And so, except at the 25 millimeter, the white end peak, so that T equals 255, actually increases directly proportionally to the nominal maximum aggregate size. So the very top values there, 255 on the graph on the left, those are the largest aggregate sizes, and then they go down significantly as the nominal maximum aggregate size decreases. But this is relatively similar trends here that we saw in the uniaxial. The only difference is that that 37 drops a little more. There's a little bigger difference between the 27, or excuse me, the 25 and the 37.5 aggregate sizes with both the mean values and the A/M. And then finally with the torsion bar, grayscale analysis, you can see here that the trends continue. The 37, 25, and 127.5, or the 37.5, the 25, and the 12.5, there's a very, very strong parabolic shape with the largest values by far at the 25 for both the mean values and the A/M. But there's also relatively high standard deviations at these values as well. And what we've seen here, we believe, is that a single aggregate really has a high chance of dominating a specimen. So if you're cutting these very small torsion bar samples that are 12.5 by 50 millimeters, and you literally have an entire 37.5 millimeter nominal maximum aggregate size aggregate particle within that sample, that single aggregate really, really can dominate your specimen. So let's do the same thing for the grayscale analysis that we did for the dynamic modulus data, and let's look at these lines of equality. So you can see here's the A/M ratio for the IDT configuration on the y-axis, and the A/M ratio for the uniaxial configuration here. And you can see both the 25 and the 37 millimeter nominal maximum aggregate size mixtures fall above the line of equality. And so some warning bells that went off is perhaps did the IDT configuration not accurately represent the composition of the mixture? And we found that both of those two aggregate sizes actually had the higher A/M than the uniaxial configuration. A conclusion from this analysis is the difference in the A/M ratios of the same mixture, but using different aggregate sizes, different specimen sizes, could actually help identify representative volume element. So we think that there's something that could be going on here with these larger aggregate sizes that could perhaps indicate that these larger aggregates may not be appropriate for the IDT configuration. And this really pops out also when we look at the torsion bar versus the IDT. So now we have the torsion bar A/M ratio on the y-axis and the IDT configuration on the x-axis. And all of the ratios clearly fall above the line of equality. And you have the higher A/M ratio in the torsion bar configuration. And we're asking the question, are these aggregate sizes inaccurately influencing the mixture composition with these smaller sample sizes? If all of these are that high above the line of equality, that could potentially be a red flag. And we feel that representative volume element may not be satisfied in the torsion bar configuration for any of the aggregate sizes just because of how small a sample it is with that 12 millimeter smallest dimension. So in conclusion, our major findings is if you look at the minimum dimensions of each of these geometries, the uniaxial, the IDT, and the torsion bar, the minimum dimensions are 100 millimeters, 38 millimeters, and 6.5 millimeters. The maximum dimensions are 150 for the uniaxial and the IDT and 50 for the torsion bar. And based on these findings, we feel we can still comfortably recommend 37.5 millimeters as the maximum nominal maximum aggregate size for the uniaxial. But based on the findings, we think we should have caution using the IDT configuration if the aggregate size is above 12.5. And we feel that we really can't make a recommendation for the torsion bar, or we feel that there's just not enough data and there's too many unknowns for the recommended maximum nominal aggregate size. So we do feel that there is some future research needed, especially for the torsion bar configuration. So in conclusion, we feel that the AASHTO T342 theoretical maximum nominal maximum aggregate size is appropriate as it's written in the standard. We also think that there's some promise looking at these aggregate/mastic ratios. This could be a way to, if we're looking at potential specimen geometries for tests, just take a picture of it, run a grayscale analysis, and this could give us some preliminary indications, especially if you're trying to downside a test, because it could give some promising indications of erroneous influences of large aggregates. We also feel that comparing these aggregate to mastic ratios for different specimen sizes may indicate the satisfaction of representative volume element, which is important. We want to make sure we have a representative sample when we're running a test. And we do think that a grayscale image analysis technique is a viable alternative to extensive laboratory testing for evaluating RVE. The first half of this presentation was doing the laboratory testing. That took by far the most amount of time. And then doing the grayscale analysis is relatively quick compared to doing all of that laboratory testing. So I went over the highlights of this paper. If you're interested in learning more, I encourage you to take a look at the full paper, which you can find at the Association of Asphalt Paving Technologists, and all of the information there is there for the full citation. So thank you very much for joining me, and I hope you have a great day.